On the surface, doubling diagrams are some of the simplest maths you can explore. Watch this sequence for the number 11 and see if you can work out what's going on. Probably most visible is a sequence of doubled numbers where you can see 1 jump to 2, 2 to 4, and 4 to 8. At this point, since we're working in the diagram of 11, we can't double up to 16, so we take the difference between 8 and 11 away from 8. 11 minus 8 is 3, so 3 away from 8 is 5. This then doubles to 10, and from there we take the positive difference between 10 and 11 away from 10. Repeating these two steps by either doubling a number or reducing it by the difference between a given number in the sequence and the sequence's root or modulus gives us a looped sequence that brings us back to 1. For 16, notice how the format differs slightly. Here the sequence seems to drop off after 8, since 16 minus 8 is 8, and so 8 from 8 is 0. Jumping over to 3 to start a new sequence leads us from 12 to 8, and moving from 5 to 10 we fall back to 4. And similarly, with other starter numbers, all paths lead to this central sequence. Notice at this point how all our starting numbers on the left are odd, and how doubling these gives us an even right side where the sequence naturally flows. This left-right move can be more clearly seen in a vertical diagram for 32, which gives us a tree-like or cactus-like structure with a canopy of odd numbers at the top, all descending to 0 by one root or another. In other instances with non-prime odd numbers, we can find smaller loops, often split into groups of multiples. In these two examples for 15 and 21, you can see in some cases how the loops might splinter into multiples, such as these clear groups for 2s, 3s, 5s and 7s. To generalise, we could say that we take any natural number, which we'll call m, which is the ceiling of our sequence. For any number under that ceiling, we can either double if the doubling stays below m, or we reduce the number we are working with by the difference between m and our current number. If we can double, we double. If we can't, we reduce until we can double again. If a number leads back to one we already have, we can join this loop and start a new path from any number we haven't yet used. Here you can see the diagrams between 1 and 40, with a few additional primes thrown in for good measure. What's interesting to note when seeing them collectively is the shifts between loops, trees, and loops with branches. To explain some of these differences, first take a look at this table that isolates the prime factors for multiples of 2. Here we can see our earlier examples of 16 and 32, which are both powers of 2. We can think of the central trunk as various powers of 2 from 1, which is 2 to the 0, 2, which is 2 to the 1, 4, which is 2 to the second, and so on. By doubling towards an even number, we always get an even difference, and in the cases of 16 and 32, we have the difference of 2 consecutive powers of 2. Since we're doubling or shifting between powers of 2, this leads us swiftly back to 0. For other even numbers, we'll always have an even difference between our ceiling number m and the number we can't double further. Because of this, we'll always move back to another even number. And so the sequences produced contain various individual odd numbers feeding into these longer sequences of even numbers. Another note on the even sequences are the consistency of smaller loops that run back to 0. For this, we can visualise the prime factors of our sequence number m. In the instance of 22, this can be broken down into 2 times 11. The highest prime factor will always form that 0 loop. In this case, 11 drops back to 0. In the case of 26, we have a 0 loop from 13, and for 34, there's a 0 loop from 17. We can also see how the pattern structure for even numbers expands as we double our ceiling number. Take the shift in patterns from 5 up to 40, where 5 doubles to 10, 10 doubles to 20, and 20 to 40. For 5 we have a single loop of 4 numbers. 10 can be seen as a loop of 4 numbers, with 4 branches containing one odd number each, and a separate 5 to 0 loop. 20 is also a loop of 4, with 4 branches of 3 numbers each feeding into it, and a separate loop of multiples of 5 running to 0. 40 consists of a loop of 4 numbers, with branches of 7 numbers, and a separate sequence for all multiples of 5 below 40. Now let's have a look at odd numbers, but not primes just yet. As with even numbers, the first thing to note is that with an odd ceiling number, when you can no longer double, the difference between any double number and the ceiling number will always be odd. From here, the easiest way to understand how odd numbers work in these doubling diagrams is the same as with even numbers, to break down a given number into its prime factors. This way we isolate the construction of a number and can predict the types of loops that will appear. Look at the examples for 15 and 21 that we saw earlier. For 15, our prime factors are 3 times 5. What we can see is a loop containing multiples of 3, another loop with multiples of 5, and then 2 other loops containing numbers that can be seen as prime to 15. That is, they're neither its prime factors nor multiples of its prime factors, so don't divide into it in any way that gives either clean integers or simple fractions. For 21 we have prime factors of 3 times 7, so we can imagine loops with multiples of 3 and 7. In this case there are 2 loops of multiples of 3, one with multiples of 7, and 2 other loops with numbers prime to 21. In our cases for odd numbers, any numbers prime to m appear in loops of equal length, so in 15 we have 2 other loops of 4 numbers, and in 21 we have 2 other loops of 6 numbers, all with numbers prime to our ceiling number. This looping in multiples becomes more apparent with larger numbers. Here the loops of 33, with prime factors of 11 times 3, can be more clearly seen. We have one loop with multiples of 11, another with all the multiples of 3 under 33, and then 2 remaining loops of equal length, all with the numbers prime to 33. A simple explanation for these loops is this. If any number is a multiple of the prime factor of m, then the difference between any given number and our ceiling number will always be a multiple of that prime factor. So in the case of 33, if we have a number that's a multiple of 3, its difference from 33 will be a multiple of 3 too. If the number is a square or cube, i.e. it only has one prime factor, then all numbers that are not multiples of that prime factor occupy a single loop, seen in the case of 25, which is 5 squared, 27, which is 3 cubed, or here for 81, which is 3 to the 4th power. In the final instance, we can look at prime numbers as the resolution to these doubling diagrams, where some cases produce a perfect singular loop. The first thing to note is that all primes form loops, either single or multiple forms with no branches. And as with odd numbers, we also have an odd difference between our prime number and the number we've been doubling. However, in this case, this difference is never a consistent multiple, like we saw with the case of 33 and multiples of 3. So if we look back at our earlier example of 11, we can see differences of 1, 3 and 5 from doubling. Also a note that the even differences that you see are from reducing once, not of doubling. Since we can't take prime factors of a prime number, our best trick is to reduce the prime by 1, and then consider the prime factors of this number. Here you can see a breakdown of the primes up to 100, with p minus 1 and the prime factors for this number. Not all primes culminate in single loops, as can be seen with 17 or 31. So what's the reasoning behind these perfect loops that we see for numbers like 11, 37 and 83? In short, they all share a primitive root of 2, seen in this right hand column. But what is a primitive root? I'll link a few extensive explanations of primitive roots below, as this will be a simple explanation for our specific example of doubling. Because we're doubling, we're always working in powers of 2. So rather than thinking of reducing and going backwards, I want you now to imagine that we're moving around a clock face, continuously doubling as we move forwards. For every power of 2, we want to move around our clock face that number of steps. Our clock face can have any amount of numbers, which is called the modulo. So if we're working in a loop of 11, rather than 11 being our ceiling number, as I've described, let's think instead about continuously cycling around a clock face with 11 points. We start off at 2 to the 0, which is 1, we move to 2 to the 1st, which is 2, 2 squared, which is 4, and 2 cubed, which is 8. Our next number in the doubling world is 16, which is 2 to the 4th power. Yet we don't have 16 on our clock face, so instead we jump around another 8 steps from the number 8, which on our 11 clock face lands us at 5. From here we can do the same with 2 to the 5th, which is 32, moving 16 steps around our 11 dial clock, which leads us to 10. Doing this all the way to 2 to the 9th will land you at 6 without repeating or landing on the same number on our clock face twice. And if you continue to 2 to the 10th power, we land back at 1 again. You can run the same procedure with an imagined clock face of 13, 29 or 83, which would take some time, but you would see the same result, where no number is landed on twice, giving us this perfect loop of numbers. What's described as the modulo is often seen as a remainder when dividing one number by another. So in the case of 2 to the 4th power, which is 16, in mod 11, our remainder is 5, since 11 goes in once with 5 left over. For 32, 11 goes in twice with a remainder of 10. For primes that loop more than once, such as 17 or 31, you'll see how doing this operation means we land on 1 twice without having jumped to all the other numbers. For 31, this happens to be pretty quick, since the remainder of 32, or 2 to the 5th, in mod 31 is 1, so we consider this not to have a primitive root of 2. Modular arithmetic such as this has many day-to-day uses that underlies cryptography systems vital for modern commerce. That's because this mathematical operation is easy to do forwards, but it's near impossible to do backwards. Imagine someone giving you the number 7 and asking you what number that came from. Of course, it could be a whole host of numbers, which unless you had some kind of prior knowledge, or specifically the modulo we're working with, you have no way to find out. And imagine now if the modulo is a huge prime number, then we're really stuck. So that gives you an overview of doubling diagrams. A full proof can be found in the link below if you want to dig further into these loops, along with some other links on modular arithmetic and encryption, which explains the last bit in a bit more detail. Like and subscribe for more of these kind of explainer videos, and thanks for watching.